Actually, let me go to Remy. Remy asked about the fourth order Riemann-like tensor, and Jack, that would give the opportunity to do the scribble on the iPad screen.
Okay, let me get back. Let me get back. Okay, I have to now get it again. I lost it. What? No. Ah, there we go. Screen mirroring. Yeah. Okay.
Hi, Jack. Good
Wait,
good
okay,
presentation.
now, hang on. Let me just get
Yep.
get it. Okay, Mac. Wait, no, okay, so now do I have it? Let's see. Okay, yeah, you see, good. Oh, that's my hey, let me see what happened to do that. Oh, there we go. Yeah, look at that. All right,
Oh,
so
it
now-
looks like screen sharing might have gone off on it.
Yeah, no, wait, no.
There we go. Okay.
No, that is, no, that, now I want to get my, there we go. Okay,
There we
so
go.
now, all right, now, there's papers, there's Matt Visser. Wait, let me. Matt.
Yeah,
Visser,
he's well known. Yeah.
Visser, and there are two guys, Medina. You just go Medina, Stephanie.
Okay.
This is all archive, ARXIV. Okay, just look at them. Okay,
So his name,
and
yeah.
now let me go. All right. There's okay. I'm gonna use Matt Visser's notation. Calls it Z A B C D. This is a fourth rank susceptibility tensor for all matter, all electromagnetic susceptibility tensor. And for example, this is fourth rank, and this is for the EM, electromagnetic response of any material, in principle, any material to an input electromagnetic field. Okay, Z0, I think I0J. Okay, A, B, C, D, those go 0, 1, 2, 3, 4. The I and J just one a space-like, In other words, you have like these are space-like, time. You have here. This is called this is called what do they call that vector? The time-like vector. And there's a shift vector, and J. There's the ADM formalism.
Yeah.
Okay, this is epsilon ij permittivity.
Okay.
Okay, then there's stuff with the anti-Semitic, there's the space-like stuff, it's the permeability, there's all kinds of other stuff. You get all kinds of stuff in anisotropic materials. You can have, you apply an electromagnetic field here, you get a magnetic field there, or, I mean, there's all this complicated stuff, but every possible physical effect, electromagnetic response effect to an external EM field in any material can be described by this tensor. Okay. And by the way, this tensor is a pure number. It's a complex field. This is a, this is Z A B C D. It's complex. I can't draw complex tensor field.
Yeah.
Okay. So it's Z A B C D. It's like in polar, I'll use polar rather than B, C, D, E to the I, R, Z, A, B, C, D. It's a complex field, okay? It's space and time, right? X means space-time. All right, now, what Keith Wands and I have done, okay, so let me tell you how this first happened. The history of this, 2011, General Pete Warden, USAF Space Command, takes over. He retires from the Air Force, takes over NASA Ames. NASA Ames.
Okay.
Okay. NASA Ames. NASA Ames. Okay, and one of my former, a guy, he was kind of an informal student of mine, younger man named Creon Levin.
Mhm.
Is kind of Pete Warden's right-hand man, his assistant helping to run NASA Ames, okay? This is like, when is this? I guess, yeah, around 2010. It's around 2010. 2010. Okay, so, and then there's this guy, Doug Trumbull. Let's make this an interesting. Doug Trumbull. Does anybody know who Doug Trumbull is?
Sounds like the guy from 2001. Was that the special effects guy?
That's special effects.
All right.
2001. Doug Trumbull, guess what? Doug's very into UFOs. He's a UFO nut. Doug Trumbull, who I know through Marshall Nafee. Who is Marshall Nafee? Marshall Nafee, there's a whole, I could go on for, okay. Marshall Nafee was a billionaire, United Artists Theaters, one of the creators of Comcast, Liberty Mutual, he's real, captain of industry, close friend of Ronald Reagan's, and a guy I used to hang out with. Okay. Doug Trumbull, I guess it was the 1980s, Doug Trumbull worked for Marshall Nafee back, they were trying to develop some kind of camera, some kind of super cinemascope camera. And so I met Marshall Nafee flew me and Kim Barafato, this in the 1980s, I guess, was down to Hollywood to meet, to Doug Trumbull's place. And that's how I met Doug Trumbull through Marshall. And there's more to talk about Marshall Nafee later on. But so in any case, Doug Trumbull comes to NASA and I'm sort of shepherding him around. There's a meeting at my place, in fact, where I am right now, Pete Warden, Doug Trumbull, Creon, other guys. And what Doug is trying to do is to get NASA to fund UFO research. Okay. Because Doug Trumbull, being an optics expert, what Doug Trumbull did, he developed a mobile unit, like a Land Rover with all this stuff, frequency shift that they could have, he could have measured the anomalous frequency shifts from UFOs that I'm talking about. With cameras, all the latest stuff back 10 years ago. Had all this his own money, Doug Trumbull's own money, a mobile unit, and wanted to have a whole bunch of these things to track UFOs. That's why he was there. Okay. So, all right. So what happened? Then what happens is they set up the 100-year Starship, 100-year Starship. Was being set up. And this was a thing to try to, a project to get to the stars, right? And there was an initial meeting, 30 people, Jack and others. I was invited, spotted with Peter Diamandis. Is it Peter Diamandis? Yeah, it's Peter Diamandis. It's Diamandis. Who's the guy who did the genetic code, down in Southern California? I forget his name.
Watson.
Craig Venter. No, Craig Venter.
Oh, yeah, that one. Yeah.
Craig Venter. All kinds of stuff with the long, guy, the Rockefellers, all these. Oh, well, what's his name? All the hippie. Who's the hippie guy? The cat. Oh, in any case, all these, a lot of these progressive guys, a lot of these important people who are around Jerry Brown at the time and now, I guess, a lot of these Democrat guys. In any case, they're there, but high techies, the techie people, Silicon Valley people. Okay, so there's a meeting. All right. They set up a meeting in Orlando, Orlando, Orlando. This is now October 2011, and it's DARPA, NASA thing at the hotel. The general warden invites me to give a talk.
Mhm.
They pay me. He pays my airfare and my hotel. Down to Orlando.
Mhm.
And guess what? My paper is about UFOs, low power warp drive, and metamaterials.
Mhm.
This is October 2011. Okay, and metamaterials. And you can read about this. Sharon Weinberger. See now, Weinberger, she's a defense journalist in Washington, defense analyst, journalist. She's written a bunch of books. She writes. She wrote a BBC. There's an article on the BBC website about Jack Sarfatti, UFOs. So what happened was, I give this talk, and I'll show you what the physics was in that talk. I give this talk, and guess who's there? Guess who's there? The same people. Eric Davis, Mark Millis, John Kramer, John Kramer, Doug Trumbull, a whole bunch of people, about Doug Trumbull. And a whole bunch, and the Russians. Russians are there. Of course they're going to be there, right? Not advertised, but the Russians are there. Russian agents were there, right? And so what happens? I start saying that flying saucers are low power warp drive, and they're using metamaterials to do it. Eric Davis and John Kramer, Mark Mills, they all get very upset. They say, "Oh no, we don't want to talk UFOs here. No UFOs." The article by Sharon Weinberg in the BBC tells all about the big stink, the big mess I made by bringing it, because they're all afraid of being late. Even though Eric Davis, we now know, Eric Davis, one of the big UFO guys, right? He's pretending he's not interested in UFOs. I'm telling the truth. Eric Davis is lying. He's like, Eric Davis, like Joe Biden saying, we won in Afghanistan. Okay. All right. Yeah. So, and then what happens? Doug Trumbull comes to my defense saying he thinks this is a legitimate. So there's a whole fight going on there. And the next day too, that Doug Trumbull's the only guy who defends me. And all the others, they're scared. No flying saucers. Oh, no, because they're afraid they won't get any money. They're just trying to, they're afraid it's too crazy. All right. Okay. But then what did I have then? The equation I had then wasn't quite right. The equation I had then was G mu nu equals 8 pi G over C to the fourth. But then I had like the 1 plus chi E, 1 plus chi M squared. Yeah, I had like the modification of the modification. Okay, what is, remember, C squared is 1 over epsilon 0 mu 0. That's the vacuum, okay? And this is the modification. Okay, what this is, that's all from E plus E minus photon scattering. That all comes from, mainly from the scattering of photons through the ZPF, the ZPF. What Hal Puthoff likes to talk about, the vacuum polarization, the virtual electron-positron pairs. But I claim that inside material, you have to include the real charges. Okay, now the problem with this was not invariant. Although they didn't know that, the guys, they were just like going, oh, like this, I don't want to hear, no UFOs. So they hear UFOs, their minds close off. They panic. They piss in their pants, the whole thing. Okay, so there it was, and that's where it was until about 2019, and that's when Keith Wanzer, who's an expert in he knows all this dielectric stuff, and he said, well, it's not invariant. That's a valid thing. And then I think it's not invariant. Then I found Medina Stephanie papers from about 2017 that came out, where they basically had the same tensor that Matt Bissa has, A, B, C, D. Okay, found this tensor. So I said, now here's the logic. Here's the logic. Einstein's equation. It's a tensor equals a tensor. And there's a coupling here. That coupling has to be a scalar field. Because it has to be locally invariant. You see, a scalar field can be variable, can change, from X to X. I mean, I have a scale, I'll call it S. S of X not equal to S of X prime, where X is not equal to X prime, but it's still locally invariant. See, people don't understand. They don't understand. Well, they don't understand tensors. They don't understand anything. See, what happens if I have an X here and an X prime there, okay? In general relativity, the transformations are local transformations. I have like this. I have Alice. I have Bob. Okay. And what they're doing, their light rays are going, this is Alice's world, this is Bob's world. So photons are going, real photons are going to here, to Alice, and they're going here, okay? And Bob, computes a tensor, I'll call it G UV of X. And Alice computes G U prime V prime at the same X, okay? But then the transformation is between these two guys here. Transformation is G mu prime V prime X, the same X equals X mu prime mu at the same X. I'll call this big X. V prime V G mu at X. This is Bob, and this is Alice. The transformations, see, people, here's the thing. You look at these relativity books and these people, these guys who are computing, they can do good mathematical work, but they're mathematicians, not physicists. They don't even know what they're doing, what it means physically, operationally. They don't know what it is. It's mathematics. But this is what I mean. Now, what about over here? Over here, okay? Similarly, photons have to reach, and they compute, they do the same thing for X prime. But the transformation, by the way, Alice and Bob have to be what's called local coincidence. Let me go to next. Einstein, you have to read Einstein. Whole problem. Alice and Bob, detectives, they're local coincidence. What is the basic physics problem in all relativity, whether it's special relativity, general relativity? You have two observers, Alice and Bob. They're using light signals, far field light signals, radiation, to measure something that's happening out there. Okay, and they collect their data, and they use the theory. They use relativity theory, the equations, which are like algorithms, like a Turing machine, algorithms to compute what are called invariants. Or and the tensors themselves have to transform in a certain way. So the objective reality are what are called the frame invariants. Frame, I don't read my invariants. The whole idea that physics is objective means that Alice and Bob, looking at the same set of processes of events, looking at them with light signals, then compute quantities from the theory. They get numbers, and the numbers agree. They get the same numbers, right? That's how they know they've done it correctly. That's what relativity means physically. And a lot of people doing relativity or teaching, they don't even know this. They don't go, they know how to do the formal manipulation without understanding what the physics of it is, what the physical meaning of it is. Okay. So that means in the case of here and here, I can have a scalar field X here and a scalar field, that same scalar field evaluating there, where S of X is not the same as F of X prime. But when Alice and Bob compute here, they're going to get, and they do a transformation, it's going to be S prime of X. I'm sorry, no. It's going to be S of X, is going to be a local transformation here, is going to go of S prime, X prime, which turns out is going to be S of X prime. It's at the same numerical value moves over here rather. No, okay, no, I did that. No, I did that. See, even now I can do that. No, that's not right. Forget that. Forget what I just said. I said it wrong. Let me go on that one. What is it? It's X. Let me do it. Sorry, let me do it again. It's X prime. It's, I'll call it Alice and Bob. This is what I want to do. Okay, Alice and Bob, and but they're using light signals. Okay, now, so I have S of A. Here's S of A at X goes to S of B at the same X. S of B at the same X, but S of B at X equals the numerical value S of A at X. That's what I meant to say. See, over here, they're the same. But if they do it over there, it'll be different. Here you're going to have S of A of X prime goes to S of B at X prime, which is, but that's equal to S of A at X prime. But S of X for any observer is not the same as S of X prime. See, whoops, back. This is a subtle concept because even people like Kevin Knuth, I think, I'm not sure Kevin, but James Woodward is very confusing. He doesn't get this. A lot of people, they don't get this. They say, oh, speed of light has to be constant. Thinking special relativity, uniform, they don't understand what a scalar field is. So a scalar field, and even I got confused trying to explain it to you, right? For a moment, I forgot, all right? Your scalar field, it's locally variable. It's not the same at different points in space and time, or different events in space and time, but it's locally invariant. In other words, if two different observers try to measure the value of that scalar field here and now over there, they try to measure it, they're going to get the same number because it's a local frame invariant. Although over here it's different, it changes. Now let's get back to what Einstein did. So what did Einstein do?
So it was a correspondence principle. He just wanted to get the vacuum solutions to match.
Yeah. So here's what Einstein did was this. Einstein had G mu nu at 8 pi and X. He doesn't know what X is, right? And T mu nu. And in particular, we go, the Newtonian limit is the zero, is the time component. 0, 0 is equal to 8 pi X T 0, 0. Okay? So what happens is, if you do the tensor calculus, G 0, 0 goes to, I think it's 2 del squared Newtonian over C squared. That's what that is, okay? And that has to go over, and Poisson's equation is this is equal to G, I think 4 pi.
4 pi in there,
Yeah. It's equal to 4 pi G rho. That's the mass density. In fact, that's the mass density. Okay. So, so in order to do that, in order to get that to agree, if you do the math, in order to get to agree, if you take G over C,
yep,
you take G over C to the 4th.
That's right.
Yeah, G over C to
yeah. He's got a C square in the
and then because T 0, 0 is equal to rho C squared.
Yeah.
Yeah. Okay. So that's how we get it. So that's how we got it. But the C, it's purely empirical. The only thing you do need that this is an invariant. It's got to be an invariant. But this is a trivial invariant. Yeah, this happens to be an invariant, which is the same everywhere in space and all over matter. But there's no compelling physical reason for it to be that, because what it can be.
Yeah, I'm digging it, Jack. I'm digging what you're saying. And
well, just let me finish my argument.
Sure. Yeah.
Let me finish my argument. What it can be, all that's required mathematically, 8 pi C to the 4th, G. This is for dimensional reasons, and then I'll have an S. I'm going to put an X. X T mu nu X. These are okay. Where this is, see, this whole thing at fixed X, see, this is what's important, at fixed X.
Yep.
Where the at fixed X, S is invariant.
Yep.
So, okay, but it could be different inside material. It's different in different locations in the crystal lattice. It can be different, but it's still invariant. So this is still a kosher tensor equation. And now, okay, and now, wait, and now then the trick was, and now this is Keith Wanzer, okay? Keith Wanzer. See, he fixed my thing. He said your equation, it's Z A B C D Z A B C D.
What is the connection of that?
Wait, let me finish. I'm not finished. No, don't interrupt me mid-string. I have a coherent sentence. I have to finish my sentence, put a period there, dot the I's and everything, okay? So now, in particular, in a simple case of a homogeneous isotropic material, okay? Keith calculated, went through everything, you know, I mean, it's a lot of calculation. He went through the actual tensor, all the component. And in a simple case, S equals 1/2 epsilon 0 squared plus mu 0 over mu. It's a homogeneous. Any material, this is true for any material, homogeneous isotropic material. This, now notice one thing, this is now Keith's discovery. Mu is the magnetic permeability. When mu goes to 0, this thing goes infinite.
Yeah.
Diamagnetic, okay, wait, let me do it again. S equals 1/2.
Yeah, I can see you contracted these things. I can't see the generator.
Mu 0.
What do you get?
And mu. Wait. mu goes to 0, S goes to infinity. Mu goes to 0 in superconductors. The Meister effect, superconductors.
Okay.
Meister effect.
Yeah,
Expelling.
super diamagnetism. Yeah.
Okay, this is just a rough thing. This is I mean, it's not going to really be infinite. Okay. So now, but when S is big, so here's the main idea of warp drive. If G mu nu equals 8 pi G over C to the 4th S T mu nu, if let's just roughly, if S goes to infinity, for a fixed, keep G mu nu fixed, we have a desired warp field we want to make. A desired warp field, T mu nu goes to 0. That's the basic simple math idea. It goes to 0. That's the basic idea of low power. Low power. Low power warp drive. Okay. So the point is, you're beginning to see that's the basic, that's the math of it. Now there's a lot more, because I'm leaving it, there's a lot more. It turns out, this is called the Hawking-Unruh effect. Basically, what the Hawking-Unruh effect says is that the distinction between real and virtual electric charges depends upon the proper acceleration of the detector. So that means the very nature of the quantum vacuum, the boundary between real and virtual charges, is contingent. It's not it's a relative thing. It depends on the absolute on the proper acceleration of the detector. So this means if you're calculating the coupling of electromagnetism to gravity, you have to include all charges equally. It's like a Copernican principle of charge. You can't only, the speed of light in vacuum is only the virtual electron-positron pairs inside the quantum vacuum. But as soon as you go to an accelerated detector, which is a transformation of general relativity, as soon as you go to that, what's a virtual charge for Alice is a real charge for Bob. It's like the electromagnetic fields, the way they transform too. Okay, an electrostatic field in the rest frame of a charge. When you go to a moving observer, it's like a charge in motion. It's like a magnetic field. All that kind of stuff. Okay, so the point is, in order to be consistent mathematically with covariance, with the tensor calculus, you have to include this. You have to include what the S field does. The S field includes the real charges together with the virtual charges. In other words, this is it's like a screening. It's like a screening factor, like screening.
Yeah.
It's like it's like Q squared over 4 pi epsilon R squared, the Coulomb force. Where epsilon, instead of epsilon in vacuum, goes to epsilon in the material. It's very much like that, but that's it's a special case. This is a generally covariant version of that. It's basically the screening. It's what it's doing, what our S field does physically. It integrates in a consistent way the interaction of the input photons, real or virtual, with all the charges, both real and virtual charges, because that, the boundary between what's a real and virtual charge, they transform into each other under general coordinate transformations. So you have to have this. So it can't be the speed of light in vacuum. That's stupid. It's totally stupid from almost every point of view. Okay, I'm going to take a quick break because I'm going to run to the bathroom and drink some water. Why don't you guys, let's take a quick.
Get some water.
Okay. Go for it, Jack. And then actually when we come back, we'll go to Jeremy Rees.
Talk with you.
Is everybody getting that? You getting that?
Yeah, and we're getting a lot of great feedback. Thank you for asking the questions. And
we Jack and I, we were with his group, Joseph and a few others. They were digging at him. Jack was being his usual self, very how do I put it, very forthright. so he's pissing them off. But I'm beginning to see what he's saying there. This S needs to be there, just because of this Hawking-Unruh effect. Yeah, you need to bring all kinds of charges, virtual and real, under the wing of this effect, and it should be in relativity. It should be in general relativity.
This
And
is
he's
amazing
also-
stuff. Like
Oh.
nobody accounts for that in any equation.
Sorry, who's that?
Oh,
excuse-
sorry, that's Lulu. Hi, Lulu.
oh,
Hi.
Happy Saturday.
it's not a happy
I
Saturday.
hope I did a good enough intro for September 11th. I didn't write
Yeah.
notes on that, so I kind of dropped
Yeah.
the ball.
So Lulu, what were you saying?
I said most equations don't include the detector, as part of it in any form. Not, and here, the detector is in motion as well. Yeah. So motion does.
It's like what they call fiducial, isn't it? Fiducial hypothetical test particle which tends to zero. I mean, they try to, as you say, try to take out the effect of any detector. Yeah. But I think the point Jack is making here, there are effects. The history of relativity is to do with astronomy, and you're dealing with it. Just follows on from Newtonian cosmology. They're dealing with point masses. They're not considering anything happening inside a material. So it's totally legitimate in this century to be considering relativity inside materials. And then all the purists are saying, well, how can any of this be invariant? And Jack has explained how you can have something which varies, but locally is still invariant. So I concede on that. And then this whole idea of S, which I'd like to see the derivation. I'd like to know how he gets it from this fourth rank tensor, how he gets this neat S function. I'll have to look into the source papers of.
Okay, now I'm back. So
Oh,
that
right.
is not, okay, that's the work of Matt Visser and his
Right.
group. The fourth rank tensor is standard. Apparently, oh, wait a minute. Apparently goes back a long way. Somebody's found a reference, I forget, a guy named Doyle. This fourth rank tensor is well known to solid state dielectric type people. It's a standard thing.
Okay.
It's called a covariant. Yeah, it's called covariant. There's a whole bunch of books and papers on it. This is not Jack Sarfatti or even Keith Wanza. The fourth rank tensor susceptibility is, there's a literature, and it's experimental. I mean, it's engineering, it's electrical engineering, solid state engineering. Now, putting the way we could, the scalar field, the contraction, that's original. That's Keith Wanza and me. Doing, in other words, okay, let me say it again. Z, A, B, C, D, that's a long history, a lot of literature on that, okay?
Okay.
Saying that S equals Z, A, B, C, D, Z, A, B, C, D,
Contracting down.
and that G over C to the 4 goes to G over C to the 4 over S, that's Sarfatti and
That's original, yeah.
Wanza. This is Visser,
Okay.
and Medina,
Can
and other people. There's a whole bunch of, you could find that in the literature. That tensor is well known.
Okay.
Computing, what Keith did to compute that simple little form. Oh, wait a minute, but wait, I gotta tell you. So now, it turns out at Jack 2011 at DARPA, NASA, Jack 2011, I had G, I had G, C to the 4th, I wrote that, N to the 4th. N equals index of refraction.
Okay.
Refraction.
So it's not invariant. Yeah.
Okay, now it turns out Wanza's formula is something like, Wanza's formula is actually reduces Wanza's formula at a certain limit. It's like 1/2 N to the 4th plus 1. That formula I showed you. So I was And Keith says, Keith says, in certain limit, I was within 19% of the real, numerically, if you tried to compute things, my original thing, just intuitively, would have been within 19% of the real result. That's okay. So I was on to something. I didn't quite get it, but that's the way things go, right? I mean, my intuition was right.
Yeah, I gotta go soon, so I have a couple questions.
Yeah,
wanna
I was
ask
going to go
real
to
quick.
Jeremy next.
One was, why does the Frohlich order parameter strengthen the coupling?
Okay, well, okay, but I think right now it's the Sarfatti intuition, educated guess. I can't regular, but what I think is going to happen, I think what's going to happen, you're going to have an e to the I psi, like things, something like this. E to the I psi, like in Keith's case, epsilon over epsilon 0 squared plus mu over mu 0. No, the other way. The other way. Fuck, come on, stop. Oh, fuck.
And then the second question was, are the gravitational effects produced in the metamaterial with hyperbolic or parabolic solutions?
Okay,
Or
wait,
both?
yeah, well, hang on, just a minute. Let me get back to where I was. Okay, here's the thing. What happened? Okay, look, you have a resonance. Let me get to here. I'll give you a more a better argument. Resonance. What a resonance is, you have things like one typical resonance. You have omega squared minus the resonant frequency squared plus I gamma omega. And let me just normalize it. I'll call this omega R. You have like a resonance like this, right? Gamma. Okay, now gamma is the dissipation, right? Gamma is line width, right? Like the line width. Gamma. Okay. So what happens is, okay, so what happens at resonance? At resonance, omega goes to omega R, okay? And what happens? This goes to omega R over gamma times I. That's the Q of the oscillator, the quality factor of the oscillator, right? So what you want to have this thing as, and that's the peak height is increasing, right? The peak height in this factor here, the peak height is going as Q. So what happens, you want to have as small dissipation as possible. What happens to the Frohlich condensate? It's a long range coherence. Again, the Frohlich condensate is making gamma smaller, is what I think. Okay. Also, there's another reason for it. Okay, there's several reasons. I'm doing forensic, I'm doing detective work, police work here, because we have other evidence. We have Giovanni Modenese, and this guy Podkletnov or some Podkletnov. They are claiming gravity anomalies in superconductors. So apparently, and then Modenese has papers showing that if you have macroscopic wave functions, you have order parameter. In this case, it's equilibrium. It's not Frohlich. It's the equilibrium. The Frohlich is simply the non-equilibrium version of this. Okay. And
right, he said that there's a large diameter superconductor disk, but there's also a pulsing frequency that's part of it.
Yeah, which is the pump, like a pump, right?
Yeah,
Pump,
the pump states. Yeah, it's like excitons.
So he said, so I have that kind of empirical evidence, you see, because this is basically a Frohlich. Okay, if he's pumping it, it could be non-equilibrium. It's basically a Frohlich. It could be a Frohlich condensate, technically speaking, because it doesn't happen if he doesn't pump it, right? You have to pump it like a laser in order to get it to happen. Okay. And by the way, this gets into the weapons. You know about the gravity impulse, you know about IgG. They're claiming that here's a superconductor, zap, flattens metal. Well, you know, I mean, the impulse, they're claiming a gravity pulse travels and actually, you know, causes an effect, okay? Remember you had the guy, John Hutchinson? Maybe it's related to that. That is John Hutchinson seeing all kind of weird, you know, he has these huge voltages, huge electromagnetic pump fields, and he gets the metal is collapsing. So maybe Hutchinson is generating somehow, like Thomas Edison or like Tesla, is generating these huge gravitational pulses. And then you also have Matt Visser. They has tractor beam, let's spell tractor, repeller, and stressor beams, gravity beams, beam. He has solutions, you know, he has the general relativity, but without my S field, you know, they're weak. They're not strong, but he has a little picture of a flying saucer, zapping, flattening a cow. In his paper, he has a little cartoon of a little green man in a flying saucer shooting his gravity beam weapon and flattening a cow. And by the way, Brandon Fugel and Travis Taylor in their Skinwalker Ranch, History Channel, they have like a flattened cow that's below the ore, below the hovering object that they claim. I mean, this is pretty funny.
Do you think that they could have come across some of these waves so that they can make these beams? Are they using electromagnetic energy or something to do this, or lasers or anything, or how would you generate?
Are you talking about
Not the Skinwalker Ranch, but I was talking about Matt Visser.
They're not using anything. They're just observing it. It's high strangeness. They don't have any equipment. All they see the dead cows.
Is it possible that, like, you know, have you heard of the light craft, like Lake Marabou technology that they were working on with NASA and stuff? And there's some patents by Kevin Cremayer about shining like the supercavitation stuff. Would that be able to, like, if we did a laser, could we affect the space-time by at all with the high-powered laser, or would that not be enough?
Well, if you shine the high-powered laser on the right material, you might induce a resonance in the material that would do it. But the thing is, if it's too high power, it'll destroy the material, so that'll be counterproductive. So I don't know.
What about doing it in vacuum?
Well, no, in vacuum, there's nothing there. This is everything. Not what I'm talking about.
Everything you're talking about is inside of.
Depends on the electromagnetic, on the response of the material, the resonant response of the material to an applied electromagnetic field that's going to generate a strong gravitational field. In other words, what I'm talking about.
What about other thermal dissipative modes? Like, what about other dissipative modes? Sorry, like, for example, thermal phonons.
Wait. Wait. So I have, what do I have? I have an EM field, EM input. I have the metamaterial. And I have a gravity output. The metamaterial has an S field, and basically when the S field gets big, well, I'm not going to say infinity because I'll just say when S, and I haven't included all the imaginary parts. Well, just roughly, we want this when S greater than 1, weak EM creates strong gravity. And if this is a beam, you know, in the far field, this can be a beam. It's a weapon. This could be a weapon. directed energy weapon. High frequency, there was all this stuff that Paul Murad and all these guys are talking about, and was shut down. I was actually this was a Jason meeting, a Jason meeting in 2008. I was there, I was at this meeting, but I didn't know. See, I could have saved that meeting. The Jasons, there was I forget the names of these guys. They all claiming, these high frequency gravity beam weapon possibilities. And they were totally shut down for the same reason that space-time was too stiff. In fact, that's probably how I got the idea. That may be, that may have stimulated my thinking about this. Basically, they were all shot. That Paul Murad was made to look like an idiot. Says, when you put in the numbers, space-time is too stiff. You're not going to get anything. You're not going to get anything that could be detected. Okay? They were all, the arguments against all this, Jason, you know what Jasons are? Does everybody know what the Jasons are? Do you know what the Jasons are? The Jasons, DOD, Department of Defense, DOD, elite physicists, solving, problems for the defense, for the Secretary of Defense. When I was a graduate student at UCSD in La Jolla, for a while I worked with Keith Bruckner. Keith Bruckner ran the Jasons, the Department of Defense. So I was at a few Jason meetings back when I was in the 60s, when I was, a graduate student. And Pandolfi, Ron Pandolfi, CIA, ran this Jason meeting, had me down there. I was down there because of Pandolfi. Okay, but that whole thing, they were using G over C to the 4 vacuum. See, and that's what defeated it. In fact, there was even a meeting at MITRE. They debunked the entire concept because of G over C to the 4 vacuum. Okay, so I think that subconsciously, now I think about it, that subconsciously led me to the S field. So now everything that they were claiming, and now because of that, gravity. Okay, here's what I'm claiming. Any military guys listening? You schmucks, you. Military schmucks. Look. You know what Tic Tac can do to your fucking F-18s or your MiG-29s or whatever you're going to throw at it, your Su-35s? They can shoot a Matt-Visser stressor beam with a metamaterial gravity laser, from the Tic Tac, and it'll spaghettify. It'll spaghettify your missile coming into it, or your jet fighter, or your aircraft carrier. It'll just be like the aircraft carrier fell into the singularity of a black hole. That's the kind of technology you're up against if you don't wake up out of your, and listen to what I'm trying to tell you.
Well, Jeff, if I could mention really quick, what you just mentioned about the meeting with the HFGW, Gary Stephenson, and he might actually be in the conference. He had said exactly the same thing. He had said, and this was when you spoke earlier at APEC, Gary had said, if we had known about the metamaterials back during that meeting. So he said exactly the same thing you said. I just thought I'd put that out.
Yeah, well, because it's obvious now that we didn't have that idea yet. We didn't have this idea of changing the coupling. And the reason I got it historically was because, well, it's stupid because Keith Wanzer is, when he writes the paper, will explain the history of this is into because of the slow light experiments in superconductors. Oh, that's the other thing. See, superconductors, because the resonances, they slow down the speed of light. That's part of what's going on here. It's more than that, but that's part of what's going on here. Okay, so that gave me the idea. That was just an idea. So, well, the superconductor, that's a for the condensates, also like a superconductor. If that slows the speed of light, that enhances the coupling. So that's what's the original idea. And now it's gotten more, more rigorous because the fourth rank tense is all that. But that was the original idea. Okay. And I think if I hadn't gone to that Jason meeting, if CIA's Ron Pandolfi had not invited me to Jason meeting, I might not have gotten this idea. So it's all kind of like, it's all being programmed, programmed from the future, destiny, it's all, because remember they said, I don't, and when I was a kid of 13, the alleged conscious computer aboard the flying saucer said that they were programming me to create their technology. And not me, others too, like Al Puthoff. Well, the others who I begin to meet in 20 years, they were also part of it. It's a whole group of us they selected. We were kids. in the 1950s. Okay, so maybe that's what's happening. That's what I think. That's what I think personally is happening. Because there's too much woo, weird, really high strains of stuff in the sense of Jacques Vallée paper that's really going on here. This is not coming out of the, this is, there's a whole context here. I'm basically channeling this information.
Tim, when are we going to get
Take it
Ron
seriously.
Pandolfi on?
What?
We got to get Ron Pandolfi to come on too, man. That would be great. Thank you, Jack, for that. That's really interesting history. I think I heard about Jason years ago, but thanks for reminding me about that. I'm going to have to dig into that a little bit deeper. That's super interesting.
Yeah.
Wonderful.
Yeah, you should invite Ron to talk. I don't know. Yeah. Okay.
Yeah. Well, so let me ask and see who else has questions. And so we're coming up on just about 3 o'clock Pacific. So Jack, that's close to 3 hours, sir. I don't want to take too much of your time.
If somebody has an intelligent question, I'll yeah. I'm having my little Johnny Walker here, and that gives me an added energy. It's the first drink I've had. This is the first drink I've had in over a week because I had a booster shot. I had to have a booster shot for the COVID vaccine because I'm flying to London in a couple of weeks, about 2 or 3 weeks. I'll be in London till the end of the year. So yeah, in order to fly, you have to get these damn shots. And I need
Cheerio. Right. What I was going to say, about another question about the thermal phonon modes. Thermal phonons, would those contribute to gravity effects, or would energy be expended?
You mean if you have like a Frohlich condensate of phonons? Yeah, they might. Yeah, piezoelectric. Yeah, all that. Oh yeah. In fact, I remember now. That's a good question because there was a lot of interest in that when Joe Firmage set us up with several $1 million in 1999 to 2000. It didn't last very long because he lost his money. But there was a guy there. In fact, the same guy. I'm pretty sure it's the same guy whose father was a friend of Kurt LeMay and all the UFO guy. That guy was also talking about generating tractor beams using pump piezoelectrics, right? So, so there might be some, there may be something to that. Oh, I should also mention that Hal Puthoff, and in his lectures, shows that slab, the bismuth, it was a bismuth, magnesium, or manganese, or something like that. Okay, that slab that allegedly retrieved. Well, it turns out bismuth is highly diamagnetic. In equilibrium, God knows what happens when it's pumped. It's tied, so that ties in too. So there may be something too. These are just clues. Like we're now it's the police. It's a mystery. It's a police mystery. Somebody's been killed, and we have little clues. We're piecing together clues, right? We're doing forensic analysis here, combined with basic physics.
I like it.
Yeah. So any more questions?
Yeah, actually, let me go to Will Riken next. Will, go for it, sir.
Yeah, in one of your things, you talk about pumping photons. Now, what I've seen in your previous presentation with your writings, it seems that you're looking at up conversion. I was wondering if you've considered down conversion, or am I confused about this?
No, wait. Try to. The audio coming from you is not that good. It's like, are you on a cell phone?
No, actually, I'm at my computer.
Okay.
Oh, yeah, he's in Japan. I'm sorry. That's.
Can you, Tim? Do you understand what he's saying? Can you translate?
Yeah. So he'd said that when he's reading through your writings, you were talking about up conversion, and he was wondering if you'd ever considered down conversion.
I don't remember when I'm talking about up conversion. It means up
photon interaction.
That's like in nonlinear optics. So what does he mean by down conversion?
Yeah, he was saying photon. Let me see. In photon interactions, so it could be nonlinear objects. Yeah.
Well, nonlinear optics is going to play a role for sure, but I'm not sure what the question is. I mean, nonlinear effects will be important, yeah, definitely. Up conversion, yeah, they may all be important. I don't.
Okay.
I'm not sure what the question is. Is non, well, if the question is nonlinear optics going to be an important thing? Probably yes. When you're doing the weapons applications, maybe when you want to generate, the tractor beams and the repeller beams and the stressor beams and Matt Visser, I could see there might be converting a high power far field radiation laser input into a gravitational. Yeah, that would make sense. Roughly, that makes sense.
Okay.
I mean, you're probably going to need, you're going to need nonlinear effects for sure. For sure. So I said, roughly speaking, I say yes. Why can't I get this now? Yeah.
Thank you. Let me go to Kate next.
Oh, hello. First off, this is absolutely amazing. I was just wondering, because you did briefly mention that Jim Woodward didn't understand everything. If you had done any research into his mock effects drive, because I know he's having more success with that, and just what your thoughts are.
Well, my thoughts are this. Let's suppose everything Jim says is correct. Okay. It's still not going to be that helpful in terms of space exploration, because it's an impulse drive. It's just like it's like an ion drive without the ions being spewed out. It's like a propellerless propulsion, but it's off geodesic. There's G-force, and it's still going to be very weak. It's still going to take you 1 million years to get any place, and there's going to be time dilation problems. And it might be useful to get to the moon or to get to Mars. Okay, that's assuming it works. But now, Keith Wanzer, who is a full tenured physics professor at Cal State Fullerton in the same department as Jim Woodward. Actually, no, Jim Wood. Got to remember, Jim Woodward degree, his PhD is not in straight physics. It's I think it's in the history of physics and philosophy or something like that. So he's kind of partly a self-taught experimentalist. And Keith Wanzer, who's in the same, who's a real tenured experimental physicist, worked with Joe Weber and all that stuff, has found what's wrong. He found flaws in the experiment, the actual experimental. So what I'm pretty sure Keith and even Eric Davis, who we seldom agree with him, but even this, basically what Woodward is seeing is probably just a spurious, systematic error artifact, because it's and it's so small. Even if it was real, you couldn't scale it up to anything significant. And even if you could do it, even in the best of circumstances, it's not what we're talking about. We're talking about warp drive. It has nothing to do with warp drive.
Yeah, I was just curious because I mean he has made much increased the effects of it, and it's much better. But you think there's just no way to alter it to really make it go, or for
even if he did make it go, it's not going to help us. It doesn't explain the Navy observation. It doesn't explain the military stuff. See?
Yeah, no, I agree.
Okay.
I was just saying, is there a way to use any existing human tech to take us one step closer to alien tech?
Yeah, that's what my talk is about. Yes, what I'm doing.
Yeah, of course. Yeah. But that's why I was just asking what I understand, and that's why I'm very grateful. I was just seeing if there was any correlation between potentially any of his work. I would say that Jim is a nice guy. He's a modern day Don Quixote. He's chasing windmills. He's seeing giant windmills. But it's noble. He's noble, right? And Halford is his Sancho Panza. It's right out of Don. It's a modern day Don Quixote. And that's thank
true.
You.
Yeah, and thank you as well, Kate. Let me see. So who else has questions? Who has questions next?
Is that it? I think we lost everybody, but I think just like Socratic dialogue.
Yeah.
Stay up all night and drink them under the table, and
Jack, I sincerely, I appreciate all the time that you've given us. I just don't want to overwhelm or wear you out, and that's.
I'm fine. But the thing is this, okay, what I see this as being, I mean, the the scribbles are hard to understand, but on this may be a basis if people think about it and go back and look at the slides and think about it, and then want to come back and ask more detailed, we could get into the nitty gritty. And I should say this, what's reprehensible in terms of Eric Davis, Hal Puthoff, all those guys, Christopher Mellon, is that they're not engaging me in a debate on these topics, on these detailed technical things. See if I'm wrong, debating, they're afraid of me. They're afraid to talk to me and to, especially Keith Wanzer. Keith Wanzer, serious. He's a serious,
Well, and we'd love to have Keith on too at some point.
Yeah,
And
well,
I know he's, yeah.
Yeah, he has things to deal with. But the point is that that Hal Puthoff and Kit Green and Louis Elizondo, they have the ears of the Pentagon. They get on Tucker Carlson. Okay, they're talking to the senators. They're giving them bad information. This is the intelligence. I want to get back. 9/11 was an intelligence failure. 2021 is an intelligence failure again, because people like Elizondo and Chris and Puthoff and Eric Davis, and they're not letting my information get to the people who need to know my information. So at least to debate it, you have to have a due diligence. You get all sides of the story. They're showing their one side of the story. Now, Ron Badolfi thinks they're doing it for financial reasons, political finance. They're trying to get money. I don't know. You could ask Ron Badolfi. I don't know what that's all about. But Badolfi has very strong opinion about these people, and so does John Warner IV, who is the cousin of Chris Mellon. So there's this thing, and then we have this guy Randolph Stone, who's in the Inspector General's office of the Pentagon, who's supposed to be investigating all this. He hasn't called me yet to get he hasn't spoken to Keith Wanzer. They haven't done their job. But the Russians are and guess what? I have to mention again, I got several hundred, 300 to 400 Iranian scientists who are tracking all my stuff on the social networks, on the physics stuff. So the Iranians are into this. The Russians are into this. And our guys are, what are they doing? They're doing nothing. As far as I can see, they're bullshitting, they're hiding.
Yeah.
They're pretending it doesn't, they're doing with the UAP problem what they did with Afghanistan and Iraq. The military, the Afghan military, they're great. And they're lying, they knew they weren't. Did you hear on C-SPAN? There's some good shows on C-SPAN the last few days. This guy wrote a book, Washington Post, so I normally don't try, the Washington Post guy wrote a book, The Afghan Papers, showing how Don Rumsfeld, who actually sort of worked for Don Rumsfeld, Don Rumsfeld lied through his teeth in 2003 about what was going on. They're all lying. They're lying. Even Obama lied, and now Biden is lying. That the Pentagon, the Lloyd Austin, Secretary of Defense, and Mark Milley, that they knew that the Afghan army was a paper tiger. Most of these guys in the Afghan army, they couldn't even read. They couldn't count. They didn't know they couldn't count how many cousins were in their extended family. They couldn't tell the names of colors. That's how primitive, and they were like cavemen, okay? They're very low-level mentalities. Was the rank and file of the Afghan army.
Yeah.
So, I'm saying, as an analogy, the same thing's happening now with the UAP. We have stupid people, incompetent people in charge, and they're not doing due diligence. They're not doing their job. Well, the Russians are doing it, I'm pretty sure. Okay, and maybe even the Iranians.
So actually, Will and Jeremy, if you are open to taking more questions or having discussion, Will and Jeremy had more questions. But it's up to you, sir. It's up to
them. Yeah.
Okay. Do you want me to? Should I turn off your screen share?
No, because
okay.
the only way I can answer the question is to draw an equation, probably.
Okay.
You can ask real questions. A few words. Words are not enough. Look, physics, mathematics is the language of physics. If you can't speak the language, you can't understand this shit. You have to know that.
So I think
It's like I can't read. If I can't.
I think that's going to
read,
answer my
it's
next
all
question. I had a
Oh,
question in the
the-
chat. This is not from me. This is from my viewers. I got a lot of people on the live chat, and they I think this might answer it for them. But I want to get your official statement. What are your opinion on Bob Lazar?
He's a, well, Bob Lazar, I don't know, Bob Lazar has a checkered career. He's been in trouble with the cops too. Bob Lazar may believe what he's saying. Bob Lazar, at the very best, was a very low-level technician at Area 51.